Good morning, everybody. So today is going to be my last presentation, and I will try to change gears and talk about fermions on the lattice. Fermions on the lattice is a huge topic. Okay. Actually, fermions, even in the continuum, is like a jungle. And the Euclidean fermions, they have a lot of subtleties on their own. And of course, fermions on the lattice will not be an exception, and they will inherit many of these features. So I'm not going to touch everything, but only try to give you a glimpse of some very basic issues on putting fermions on the lattice. These issues are so basic that they have sort of slowed down the ambitious project of putting standard model on the lattice. So today, standard model, which is extraordinarily successful, its success is mostly perturbative nature. But as I emphasized in the very first talk, we need to give a mathematical definition of the theory, of the entire theory. And perturbative theory does not quite do that. And therefore, it was hoped for a long time that we should be able to formulate the standard model on the lattice. I can't go into complete details of what the difficulties are of putting the standard model on the lattice. It's still very much a work in progress, and like anything that starts with somewhat transparent ideas, the technicalities become overwhelming, and that's true for putting standard model on the lattice too. And another area which I already mentioned, related, is of realizing supersymmetric field theories, supersymmetric gauge theories on the lattice. It doesn't matter whether supersymmetry is seen in LHC or not. That's a different issue. They are an interesting class of field theories, and we would like to have a non-perturbative formulation of them. Okay? So one shouldn't take the utilitarian approach, excessively. So both these are works under construction, and I'll just basically point out to you what are the salient features of trying to put fermions on the lattice. Why putting fermions on the lattice is so dramatically different from putting bosonic field theories on the lattice. The crux of the problem is, there are two of them. One is the so-called species doubling problem. So you think that you have put one fermion field on the lattice, but if you examine it carefully, it actually represents doubling in every direction. So if you are doing Euclidean lattice, and if you are in 2 dimensions, then what you thought was one species actually turns out to be 4, and in 3 dimensions it's 8, 4 dimensions 16, etc., etc. Now that's clearly not a good sign. It screws up a lot of things, because in loop diagrams, all these additional species will contribute, and what you get will have no bearing to real life. So it has to be solved. And as I mentioned, my friend Jan Smith, already in 72, had discovered lattice gauge theories. He had discovered the link formulation, everything, But he encountered this fermion species doubling problem, and at that time he didn't know what to do about it, and he basically didn't pursue lattice gauge theories. But before I go to fermions on the lattice, I just want to add a few concluding remarks about what I have covered so far. Today, I am not going to be projecting any slides. I will basically try to use my article which I wrote. This is already 25 years old, so it's no longer up to date as to how far the problem of putting standard model on the lattice is, but it gives a fairly faithful account of the basic difficulties of putting fermions on the lattice. So I'm just going to use that and give a blackboard exposition of today's talk. Before that, just an addendum. To my coverage so far, there are certain things which I didn't emphasize about the lattice regularization. It's a non-perturbative regularization, but also manifestly gauge invariant. The whole theory is regularized in one go in a manifestly gauge invariant fashion, and that's a big bonus of the lattice regularization. And when I was looking at the non-compact version of gauge theories, where we took the vector potential, I did it for the abelian case, I took the vector potential and discretized both the continuum gauge field and the gauge transformations, and luckily the discretized action was invariant under discretized gauge transformations. But we noted a problem, and that was that if I looked at the partition function, the action is invariant under gauge transformations. Therefore, two different configurations differing by a gauge transformation would contribute the same, and there was an infinitely many configurations which were all related by gauge transformations, and therefore you would keep getting infinitely many contributions from physically the same configuration, and that partition function would blow up, okay? And it blows up. And the reason was the volume of the gauge transformation was infinity in this case. So what one does is, you will have to do some gauge fixing. Now, when you go to non-abelian gauge theories, in the continuum, you again use Lie algebra valued gauge fields, but now the volume of the gauge transformation dg does not blow up because of the Hermitian, and that is, it's a compact manifold. But you get into a different kind of problem, and that is that propagators, which are essential for perturbation theory, what do? You take some quadratic operator acting on A mu A equal to 0, but because a field and its gauge transform satisfy the same equation, it turns out that this acting on delta A mu A, so there is a zero mode and the propagator becomes singular. So you again have to fix the gauge to solve this problem. But now in our lattice gauge theory, where we don't use this Lie algebra valued variables as the gauge field, but use the links, then this partition function looks like some e to the, and each link variable is also normalized according to the Hermitian. So here again different link configurations related by gauge transformations contribute the same amount. So there is a lot of duplication. However, product at every x mu dx du, okay, sorry, the gauge transformations are g of x. Now, product of g of x at all the sides of the lattice, the volume of that is finite, because it's basically 1 multiplied by each time for each site. Therefore, it doesn't blow up, and in principle you don't have to do any gauge fixing, and that's a fantastic advantage while actually doing simulations, because you don't have to do any gauge fixing. Nevertheless, for some very technical reasons, people may still indulge in gauge fixing on the lattice, but in principle no gauge fixing is needed while doing lattice gauge theory. So these are some remarks about it. However, if you want to define a transfer matrix for gauge theories, then it turns out that it is useful to choose a gauge in which all the links along the quote unquote time direction become identity. Okay. So it's not that you don't use gauge fixing at all, but only when it suits you. But in computing, say in simulating, you don't have to do any gauge fixing. So these are some remarks which I wanted to make before I go on to the problem of fermions on the lattice. So now we go to fermions on the lattice. I already mentioned a few things that you have to treat psi and psi bar as independent variables, and the path integral measure actually involves both d psi and d psi bar. So this is more like the phase space path integral of classical statistical mechanics. You cannot write a measure involving only psi. But a more deadly problem is they have to be represented by Grassmann variables, and numerical simulation, becomes of a totally different kind, and this is one of the bottlenecks in actually pushing the precision of lattice gauge theories to higher and higher levels. But I won't worry about all that, but we will come to even more basic problems with putting fermions on the lattice. How did this, in this paper, I was motivated more by addressing how to regularize chiral gauge theories. The standard model, there are fields of different chiralities, and the left-handed fields and the right-handed fields transform differently under the gauge groups of the theory. That's the problem. Whereas in QCD, you also have left-handed fields and right-handed fields, but they transform the same way under the gauge group. Now, this is going to make a very big difference. So, we will call theories like QCD vector-like, and the standard model is not a vector-like theory. So, big question was, is there any way of regularizing non-perturbatively theories like the standard model? And various alternatives have been proposed. Some people think even, superstring theory may be the answer, because that theory is supposed to be finite, and therefore, if you can somehow embed the standard model in superstring theory, then you would have regularized it, but hardly any deep success has been made in giving a completely non-perturbative formulation of string theory, because many of these things are perturbative, and therefore that will not satisfy our goal of looking for a non-perturbative definition of the theory. So, lattice was a natural choice, and how do you do that? But much before the problem of the standard model arose, first task, of course, was to put QCD on the lattice. In fact, if you look at the title of the paper of Wilson, which introduced lattice gauge theories, it was as a theory of confinement. He wanted to understand confinement, and therefore introduced lattice as a way of studying it. So the first goal was actually to study QCD itself on the lattice, and all the difficulties that I will now explain arose right then. So let us look at the Dirac equation. I gamma mu del mu psi plus m psi equal to 0 on the continuum, and let's try and discretize this. Now the fermions live on each site, so you can continue even in the discretized version to put fermions on each site. And the natural suggestion that comes to mind is to replace the derivative by finite difference, and we already discussed how there are many, many possibilities of doing this. Now, the problem of fermions versus bosons is that the equation of motion involves the derivatives in first power. Whereas, if you look at the Klein-Gordon equation, and that will look like some, box. I may always do this sign wrong. So the derivatives occur quadratically, and that makes all the difference. So let's take the simplest choice, and that was to replace derivatives by forward difference. And the forward difference I already introduced in the early lectures. So forward difference in the mu direction of a function x. So here is x, and in the forward direction, this is the nearest neighbor in the mu direction at a distance, which is the lattice spacing. And so the forward difference is simply f of x plus e mu a minus f of x. So if I do that, then the derivative will be replaced by the forward difference divided by a. So this will become I gamma mu forward difference psi, but there is a 1 over a here which you multiply with that m to indicate that this is mass scaled by the lattice space. So both ml is now dimensionless. Keep that in mind. Now I am going to be dealing mostly with free case. So using the momentum space description is easier, and let's do that. And when you do that, what this will become so f of x is e to the I px f of p plus minus, I am not going to be very cavalier about it. So if you put it, you will get from this a e to the I p mu minus 1, and so you will pick up, and you have to be careful, you have to take back and forth difference, e to the minus I p mu, and you will end up getting sin p mu. So the Dirac equation becomes I gamma mu sin p mu plus m psi equal to 0. And you can clearly see that the continuum Lorentz invariance has been broken here, and it has been broken down to the discrete, the subgroup of the Lorentz group, which is just the rotation of the cubic group. Now this is the problem. In the case of the bosonic case, I wrote it down somewhere, maybe I erased it. Okay. Bosonic case, sin p mu gets replaced by 1 minus cos p. Remember, this p mu is p mu physical times A. So, in the continuum limit, p mu is very small because it is a physical momentum multiplied by the lattice spacing, and you would think everything is fine because in the continuum limit sin is almost equal to p mu, and you will just get back the correct equation. And in the case of the bosonic case, this is p mu squared by 2, and that also works out correctly. But now there is a problem, and the problem has to do with momentum on the lattice, which we so far didn't pay attention to. Can we have some light? Light. So, momentum on the lattice in the continuum, P ranges minus infinity to plus infinity. Minus meaning it's moving along the negative axis, positive moving in the positive axis, and the magnitude is unrestrained, and it goes from minus infinity to plus infinity. So, the space of momenta in the continuum is a real line. But now on the lattice, the momentum space, momentum goes from minus pi by a to plus pi by a, and these points are identified. So, the topology of the momentum space in the lattice in one dimension is a circle, 2 dimensions it's a 2 torus, and in d dimensions it's a d torus. Now, there is a fundamental and very important difference here, because the momentum space in the continuum was non-compact, its total volume was infinity. But the momentum space on the lattice is compact. Okay? Several topological features start playing an important role here. And in fact, Nielsen and Ninomiya pointed out why these kind of doublings happen from this topological point of view, because at some point people thought maybe this problem is because I took a very simple discretization of replacing derivatives by forward derivatives, and then there was hectic activity of various kinds, but none of them worked, and then it was realized that there is a deeper reason for that, and this is the deeper reason. The Brillouin zone on the lattice is compact, okay, and the Euler characteristic of that manifold, plays an important role. We will see this in just a moment. Can I get some light on the board, or is this all? Okay. So you may think that this equation is fine, because for small a,
Haridas. Haridas.
this goes to 0.
Excuse me. Hi. You are actually.
I don't want this.
You are being projected there.
Oh, can anybody see that?
Yeah. So that's why we did not put on light.
Okay, so should I write bigger or what?
No, it's fine.
Huh?
As long as you are fine with this,
Yeah.
we will go ahead with it. Because
Oh, I didn't even see myself there. But you know, sign vanishes not just when the argument is 0, but also when it is pi. So we have a problem. When the momentum t is close to one of these points, the sign again becomes small. And for all practical purposes, it looks like another fermionic particle in your spectrum. This is the main origin of species doubling. So now let me work out some details about this. So we will introduce a notation pi mu a. So when a is equal to 0, what is the correct labeling I have used here? Yeah. You have all 4 components which are very, very close to 0, and there is only one such. But when a is equal to 1, or let's call it mu, then you can have a pi here, 0, 0, 0, but this pi can be in any of these 4 places, and so in 4 dimensions you have 4 of those. Next I can consider what may be labeled as mu nu. So you can have pi in 2 places, and there are 6 ways of choosing 2 positions out of 4, so you have 6 of these. Then you can have mu nu rho, where you can have pi in 3 places, and there are only 4 of them. So 0 can occur in any of these 4 places, and you have 4. And finally, you have, let's call it 5, where momenta in all directions are at 4, and there's 1. So you add it up, you get 5, 11, 15, 16. So there are 16 such special momentum vectors. Only one of them is close to what you may think is a trivial case, where they are all close to the origin. Now let us examine what happens in the vicinity of this. This is okay. The Dirac equation is gamma mu I sin p mu plus m equal to 0, and all of these are small. But here, one of the, okay, so now in this case, P mu, okay, let's do it like this. Let's call the deviation as Q mu. So here you will get simply sine Q mu equal to 0. But now here P mu is of the type pi mu A plus Q mu, and in the direction where the momentum is pi, this becomes sine P mu is equal to minus sine Q. But this can happen only in one direction. So at that point, the Dirac equation is as if you have flipped one gamma mu, let's call it mu bar, special direction, so one gamma mu is flipped sign effectively and 3 have not. So you go on, it's very elementary. Here 2 gammas flip sign, and here 3 gammas flip sign, and here all gammas flip sign. So now we have the situation that sine P mu is of the form plus minus sine. Some places it's plus, some places it's minus, and the Dirac equation becomes I gamma mu sine Q mu. Q is small, Q is close to 0, plus M equals 0 plus minus. Now that doesn't quite look like Dirac equation, because in some directions it's as if you have a positive mass, some directions you have a negative mass. So we will use the freedom of defining some overall unitary transformation and bring this into the form of a standard Dirac equation. So we look for a unitary transformation SA. A stands for these labels in such a way that psi A gamma mu, SA gamma mu S is plus minus gamma mu. Where gamma is flipped sign, S will also flip the sign. Where gamma hasn't flipped the sign, S does nothing to the gamma matrix. If you do this, then the Dirac equation becomes SA I gamma mu sine Q mu plus M SA psi equal to 0, and you can call this transformed Dirac field psi A, and you get standard Dirac equation for psi A. Fine. But for each A, this represents a Dirac particle. And now we have 16 Dirac particles, but we started trying to put only one Dirac particle on the lattice. This is the species doubling problem of fermions. So how do you solve this? Before that, where Wilson solved this. For QCD. But his method doesn't work for the standard model. So we have to understand the difference between QCD and the standard model. So QCD consists of massive quarks. And each quark field can be resolved into its psi left, psi r. And so both left-handed and right-handed partners are there. But most importantly, if you examine the QCD action, and in particular how the various gauge groups, namely the color group of QCD, under the color group, both the left-handed fields and the right-handed fields transform identically. They transform as the triplet representation of SU3. This is very important. And these are called vector theories. Whereas in the standard model, you know that the left-handed and right-handed fields transform very differently. And therefore, anything that upsets the balance between left and right fields can have dramatic consequences, you know. And QCD, we will see why this is not a problem. So what did Wilson do? Wilson said, for our Lagrangian, which is 1/2 psi bar gamma mu. Now we have a gauge theory of quarks and gluons. So this is the color covariant derivative. And we will look at it when the mass of the quark is taken to be 0. And now we add a term which is m oh sorry, you don't have to do this. This is a mass term. This is a standard QCD, and he said add a term like this, where there is there's a parameter r, psi bar, d mu psi. Note that this looks like what you would add to a bosonic theory, because Klein-Gordon action has that form, phi d mu. But now we are dealing with fermions, and for the moment let's forget about all the scholarly discussion about spin statistics theorem and things like that, and just add such a term. R is some parameter. Now what does this do? Very simple to work out. Gamma mu sin p mu, which is what we get from here, m, nothing happens to it, goes to gamma mu sin p mu plus r summation mu 1 minus cos p mu. Remember I told you for bosonic fields you get 1 minus cos, and that doesn't cause problems. So you add a action piece to the fermions which really looks like that for a boson. Now you examine what happens. When p is close to pi, you examine what happens to various things, and what you will find is that the effect of this is to give masses to doublers and what kind of masses do you give? You give 2r by a for the first, 4r by a for the second, 6r by a, 8r by a, and therefore in the continuum limit this all goes to infinity. So what you have done by this method is to take the doublers which are all degenerate and break the degeneracy in such a way that all the extra species get masses of the order of the cutoff of the theory, and naively you should think that should be okay. I have banished them to very large masses, just as we don't worry about particles with Planck mass in string theory coming and affecting our standard model prediction. This naively guarantees safety from the doublers. The argument is naive, and one has to be extremely careful. So this is how Wilson resolved the doubler problem. But now comes a catch. There is something called the chiral anomaly. It's a vast area in itself, and I'm not going to try and review about it. Basically, the way it is stated is that when you have a theory with several classical invariances, like gauge invariance, global chiral invariance, etc., so because of infinities, you have to regularize the theory, and when you have regularization, you don't have too much freedom. You can either regulate the theory keeping one or the other of the symmetry. This is a naive statement because axial transformations do not form a group. Okay? So the argument says that you choose to regularize your theory in a gauge invariant fashion, and the global chiral conservation goes for a toss, and the axial current is no longer conserved, and it develops an anomalous conservation law. And this is extremely important because the conservation of the axial current now picks up a piece which is and this is extremely important in explaining why the pion decays into two photons. There has been never any doubt about the neutral pion decays into two photons, because almost as soon as neutral pion was discovered, the two photon mode was discovered. It had been studied even before it was discovered. But then all this thing about partially conserved axial current, chiral symmetry came, and it was discovered to one's horror that the standard treatment of partially conserved axial current predicted that the pi naught does not decay into two photons. Now that was a disaster, and then it was fixed by many people, Bell, Yakev, and Adler, and they showed that actually if you look at conservation of the axial current more carefully, there is a piece which is proportional to the gauge fields, and even in the mass going to zero limit, the axial current is not conserved, and it correctly explains the pi naught to 2 gamma decay. So now you have tinkered with QCD by adding that Wilson term, and you must ask, does it keep the anomaly intact? Main problem is the following, that even though these things go to infinity, if they get multiplied by something which vanishes with A, then you can end up with a finite residue coming from the Wilson term, and that's important. So again, I'll only cite the results, and you can look at my paper for some details. So you compute the anomaly on the lattice. I entered the lattice area, it's very late. You know, I'm a latecomer in all aspects of life, and it was around 1980, 81, and this anomaly on the lattice was one of the, most hotly discussed and debated topics. And Jan Smith, even though you missed out on fixing the doubling problem, actually showed how the anomaly on the lattice comes out, and it was extremely important. It not only strengthened one's conviction in the lattice, but it also pointed out that chirality in the lattice can be extremely subtle business. So the result, the lattice analog of that, del mu j mu phi, it has the standard pieces coming from this part of the action, 2m psi bar gamma phi psi. So this is the partially conserved axial current that everybody was using earlier, and when the quark masses became exactly zero, then this would be exactly conserved. When the discussion started, nobody was talking in terms of quarks, they were talking in terms of pions, and when the pions are exactly massless, then there is an additional symmetry which was called chiral symmetry. And when the pion mass is small, then this is, it is almost conserved, and therefore it was called partially conserved axial current. What about the correction? The correction looks R over A some long-winded expression here, and I must clarify what this d mu is in the Wilson mass term. So if you take an x and a neighboring point, d mu of psi is u mu psi x plus a e mu minus psi of x. Why is this form necessary? Because under gauge transformations, psi goes to g of x psi. So this picks up a factor g, but if you took only psi of x plus e mu, that would pick up g at a different point, and that would not transform properly under gauge transformations. But now this will be g and then g dagger at a different point, and this is g at the different point, and these cancel each other, so the whole thing transforms nicely under gauge transformations. So the Wilson term that was added maintained gauge invariance. This is important. So when R was exactly 0, say when m is equal to 0 and R is exactly 0, then even in the lattice, the axial current was exactly conserved. But when R is not equal to 0, a very subtle interplay is this vanishing as A goes to 0, this blows up as A goes to 0, leading to a finite contribution to the divergence of the axial current. And that's not all. Correction doesn't depend upon the exact value of R. It only depends on R being non-zero. So the anomaly in the lattice comes out correctly, in spite of Wilson tampering with the action to send the doublers to infinity. Now I have 15 minutes and I will try to explain two things. One, why this, and that is dependent on the property of chiral fermions on the lattice. Okay? We will find not only are the species doubled, but they do it in the most counterintuitive way as far as chirality is concerned. Chiral fermions. So in the continuum, you can introduce left-handed, right-handed fermions, which are some 1 plus minus gamma phi by 2 psi. Now let us pretend to put one continuum chiral fermion on the lattice. Only one. And see what happens. Put one L fermion on the lattice. So your Lagrangian is half psi L bar. This is the gauge theory. So you have gauge covariant derivative. Now some hell breaks loose because species doubling happens to this case also, and that came just by replacing the continuum derivative by the forward displacement operator and the fact that the momentum space Brillouin zone was compact. Okay? So that will affect this case also. Now let's see what are the 16 species we get. And this is the surprising thing. A equal to 0, all gammas unchanged. So gamma 5 goes to gamma 5. Gamma 5 is the product of, 4 different gamma matrices, and depending on your convention, there is an I, etc. Now let's look at the A equal to mu case. 3 gammas unchanged, and this is 1. 1 gamma changed. So gamma 5 goes to minus gamma 5. So what you thought was a left-handed fermion now, at these points, will become right-handed fermions. And there are 4 of them. And the mu nu point, 2 gammas are unchanged. And 2 gammas are changed. So gamma 5 goes to gamma 5, and it again remains left-handed, and these are 6 of them. At the third point, you're getting the drift now. 3 gammas changed, 1 gamma unchanged. Gamma 5 goes to minus gamma 5, and so this is left-handed, right-handed, left-handed, and 4 of them right-handed, and the last one, all gammas change. So gamma 5 goes to gamma 5, and this is also 1, which is left-handed. So you thought you had put 1 left-handed fermion on the lattice, but now species doubling not only gives you 16 particles, but their handedness, let's look at it, exactly 8 left-handed fermions and 8 right-handed fermions. So even though you started with, you thought you were biasing by taking a left-handed fermion, but when you put all the double species together, there's an equal number of left and right. Okay? That's the problem. So the net chirality is actually 0, even though you thought you were putting a chiral fermion on the lattice. And this is why when the Wilson term was absent, the axial current was exactly conserved because there is an equal number of left and right fields. So this is remarkable. Okay? And why doesn't it pose a problem for QCD? Because in QCD, there is equal number of left and right in the continuum, and for each of them, you will again get equal number of left and right due to doublers. So when you add up all the doublers, you again get equal number of left, equal number of right, all transforming under the same representation of the gauge group. So the vector nature of the theory is unmodified by species doubling. Of course, you have to worry about the fact that there are too many of them, and you do it with the Wilson fermions, and it doesn't spoil anything for QCD. But for the standard model, everything goes bonkers. Once again, because we have uneven number of left and right, and they transform under different representations of the group. Yeah.
What happens if we change the what if we change the gauge transformation on the lattice dependent upon the momentum of the
But you'll have to change your gauge transformation according to whether it is left or right.
Yeah.
Okay, that's difficult to do that. So I have 7 minutes. This is the crux of the problem. That the chiral fermions pose both for standard model and for supersymmetric theories. I will now end with a few remarks as to whether this is because we didn't use a very clever discretization or not. And this is Nielsen, Holger Nielsen, my very close friend, and Masao Ninomiya, who gave this topological argument that it has nothing to do with details of discretization, it has to do with the topology of the Brillouin zone. So, this problem is generic It is not because you chose some bad way of replacing derivatives by finite differences. Those days there was a lot of very, very hectic activity. There was something called the slack derivative, this, that, etc. And eventually people found none of them are satisfactory. So why is this? So let us compare a real line versus a circle. So in the lattice case, the Brillouin zone in one dimension is just a circle. Let us ask for functions which vanish. So this can vanish exactly at one point. But if you try to find a function that vanishes on a circle, say like that, because it is compact, it has to vanish some other point. Okay? So the zeros of a function on a circle come in pairs. You cannot find a function which vanishes at a single point. So this chirality is something like the points at which some function vanishes. Another better example is, take a sphere. Now let's look at a two-dimensional surface, infinite, and try to put a charge. So the electric fields go everywhere, and they can happily continue to infinity. But now try putting a charge in a sphere. The electric fields, since the space is compact, have to eventually come together. So you can't put a single charge on a sphere. You have to put them at pairs. So every positive charge has to be accompanied by a negative charge. So the positive charge is something like chirality, left-handed, the negative charge is like right-handed, and they will always come in pairs. So this is something only can be avoided if we can change the topology of the gluon zone on the lattice. And it's not clear.
Slack derivative does solve the fermion doubling problem. Because it takes non-local derivative. This, what you are saying, is property of local derivatives on the lattice.
Can you repeat it again? I didn't hear you properly.
Okay, no, just for the record, I'm saying this. You may not be able to hear it. I can explain to you during lunch.
Yeah.
What you just said is true for local lattice derivatives. If you use non-local lattice derivatives, then the result will be different.
I mean,
and that's what Slack did.
my immediate reaction is I don't believe it, because I don't think it has anything to do with non-local nature. It is more to do with the gluon zone. But this is a technical issue. I don't mind talking to you.
A Brillouin zone is not like periodic. In
But
non-local
I must also admit that Kreitz is now saying a different kind of story, and he claims that he can put the standard model on the lattice, and I don't know how he does. Maybe it has something to do with what you say. Okay. So that's the topological reason, at least as far as I understand, or as far as we understood it, as of 2000, that this is a deep problem, and now the question is, how are you going to solve this? And I'm not going to go into it because time has also run out. There are now all kinds of novel approaches that have been given, like domain wall fermions, etc., etc. These actually don't put a single chiral species in the lattice, but they put both species with controllably negligible interaction between one species and another species, so that if you are on one domain wall, it will look as if the theory is chiral. Okay? So that's the general idea about it, and there's also something called the Wilson-Gilspark method, so on and so forth. I have briefly discussed them here, but it is a very exciting problem, and I don't know what the current thinking is, but I hope I've given you a flavor of how the problem arose in the first place. Thank you.